In the previous video, I gave you an explanation of what it means to have the gradient vector with three independent variables. So now I'm going to give you an example. So let's look at this function here. Our job is to find the directional derivative of this function at this particular point in this direction. So what it means is, at this particular point, if we put 1 into the x, 2 into the y, 3 into the z, this whole thing here, so we put 1 into the x, 2 into here, 3 into here, then the whole thing will spit out the number 8. So it will spit out the number 8. So anything on this surface will spit out the number 8. So if you're here, it will still spit out the number 8. If you're here, it will still spit out number 8. So if you look at this point here, it's 1 across, 1, 2 across in the y direction, 1, 2, and then 3 across, 1, 2, 3. 3 up, sorry. So you are currently at this point here. Well, at this point here, it will spit out the number 8. So anything on this surface will spit out the number 8. So this is your level surface. So our job is to find the directional derivative at this point here, in this direction. So in this direction, it will be 3 across, 1, 2, 3, and 6 across in the y direction, 1, 2, 3, 4, 5, 6, and then 2 up. So it would be in this direction here. Okay, so to find the directional derivative, we will need to take the dot product of these two vectors. So our first job is to find the gradient vector and then dot it with our unit vector. So from here, we've got to convert this to our unit vector. So let's do the first step first. So find the gradient vector, looking at our function. To find the gradient vector, we've got to take the partial derivative with respect to x. So differentiate this whole thing here with respect to x. That will then give us this. Take the partial derivative of this function with respect to y. That will then give us this. With respect to z, that will then give us this. Now evaluate it at this particular point, 1, 2, 3. So that will give us -2, -1, and 3. So this is our gradient vector. So we've got our gradient vector. We now need our unit vector. So looking at our vector, we've got to convert this vector into its unit vector. So the unit vector is given by the vector divided by its magnitude. The magnitude of this will be 3 squared, 6 squared will be 36, 4, and then take the square root of the whole thing, it will give you 7. So our unit vector is given by this. So the directional derivative in the direction of u, so earlier I used v, but this direction is the same as this unit. They both tell you to move in the same direction. So it doesn't matter if I use v, vector v, or unit vector. They're both heading the same direction. Well, anyway, the directional derivative in this direction at this particular point is given by the dot product of the unit vector. So this is our unit vector, and our gradient vector. So this is our gradient vector. So taking the dot product will be this times this, plus this times this, plus this times this. So our directional derivative is given by this. Okay, so hang on. So what it means is what it means is this. Hang on, let me think where I am. I've lost track. So our gradient vector at this particular point is given by this. When you take the magnitude of this, of the gradient vector, so let's just imagine our gradient vector looks something like this. The biggest, this directional derivative, the directional derivative will be at its biggest. The biggest possible value our directional derivative can be is square root of 14. Is a square root of 14. But because we are heading in this direction, it's going to be slightly less than square root of 14. I hope that makes sense to you. It wasn't very well explained. But let me try and point something else out. That's quite important. We've seen this diagram before. The directional derivative of this at this particular point represents, let's just imagine we are currently here. the directional derivative represents how fast it's climbing in this scenario here. The directional derivative of this represents, well, remember it spits out, let's say it spits out a 12 here. So at this particular point it spits out a 12. The directional derivative of this represents how fast this f is climbing or falling. So the directional derivative here represents how fast it wants to climb, the rate at which it wants to climb. Up here, the directional derivative up here represents the steepness of this thing here. I hope it makes sense. It was badly explained, but I hope it makes sense.